Welcome back to AI Paper Podcasts. Today we're jumping straight into a paper called jina-embeddings-v5-text, Task-Targeted Embedding Distillation.
Yeah, by Mohammed Kaleem Akram and the team at Jina Bioelastic.
Right. And the key insight here is a brand new training regimen for text embedding models. Specifically, they're targeting compact model sizes, so we're talking under 600 million parameters.
Exactly. The secret sauce of this paper is combining model distillation from a much larger teacher model with task-specific contrastive loss. And they do this using LoRA adapters.
Which gives us two entirely new multilingual models. There's the V5-text small at 596 million parameters, and then the V5-text nano at just 212 million.
And the top-line specs on these are pretty wild for their size. They support 32K token context lengths. They match or even exceed state-of-the-art on the MTEB benchmarks for their weight class.
Plus, they have really robust performance under Matryoshka truncation and binary quantization. So let's break down how they actually achieve SOTA performance on such tiny architectures.
It's basically a masterclass in efficiency.
Yeah. Well, usually embedding models face this massive trade-off, right? For RAG and retrieval systems, you need great performance. But to get that nuance, you typically need a massive model.
Right, something with billions of parameters that just eats up your GPU memory. The goal here is pure efficiency, making these small base models punch way above their weight.
And the base models they start with are Qwen3 0.6B base for the small version.
Yep. And for the nano, they use Eurobert 210M. Both of them utilize ROPE, rotary positional embeddings, to handle that massive 32K context window.
But the real architectural twist isn't the base model itself. It's that they ditch the monolithic approach. Instead of one model trying to do absolutely everything, they use LoRA.
Low-rank adaptation adapters, yeah.
Yeah.
You have a standard transformer base with last token pooling, but then you load different adapters depending on your actual task.
Like retrieval, semantic similarity, text matching, or classification.
Exactly. And this solves what they call task conflict.
Task conflict. Let's dig into that for a second because it's so fundamental to the paper.
Sure. Think about the geometry of the vector space. If you're doing retrieval, you have this asymmetric relationship. You want a query like, say, how to debug Python to be plotted right next to a document that says stack trace analysis and error handling.
Right, the words are totally different, but they're a query answer pair.
But if you're doing semantic similarity, clustering, for example, you want how to debug Python to be next to ways to fix code errors.
Because they literally mean the same thing.
Exactly. So if you force a single set of weights to optimize for both of those geometries at the same time, the gradients effectively fight each other during training. You end up with a model that's okay at both, but great at neither.
So swapping the LoRA adapters fixes this. It's like the base model puts on different glasses depending on what you're asking it to look for.
That's a great way to put it.
Okay, so to get this to work, they use a very specific two-stage training process. Stage one's the foundation. It's all about embedding distillation.
Right. They use a much larger teacher model, Qwen3 embedding 4B. The goal is to transfer the teacher's deep semantic understanding to the much smaller student.
And to do this without needing all those complex instruction prompts at inference time, which is a huge plus. But there's a dimensional mismatch here, right?
Yeah, the teacher outputs a massive vector, thousands of dimensions. The student is tiny in comparison. You can't just compare them directly to calculate the loss.
So they use a linear projection layer. And what's fascinating here is the direction they go. They project the student's embeddings up to the teacher's dimension.
Yes. They project up, and then they calculate the cosine similarity loss. We should definitely note the ablation study here, because intuition might tell you to just project the teacher down to the student's size. It's computationally cheaper.
But projecting down compresses the information. It's like downsampling a high-res image before you let the student study it.
Exactly. You lose the fidelity. The paper showed that projecting the teacher down didn't work nearly as well. You have to project the student up, forcing it to try and fill that larger semantic space.
Makes total sense. They also had to tackle long context in this first stage. Initially, the general training just wasn't handling long documents well.
It wasn't. So they ran a specific long context training phase. They used synthetic data hiding specific sentences in noisy haystacks, as well as natural long text.
And the trick here was using a smaller theta value for ROPE during the training than they do at inference.
Right, which helps the attention mechanism generalize across that huge 32K window without overfitting to the specific token positions it saw during training.
Okay, so that's stage one. Now we have a very smart generalist base model, which brings us to stage two, task-specific adapters.
This is where things get really targeted. For this stage, they completely freeze the base weights from stage 1. They are only training the tiny LoRA adapters here.
Let's start with the first adapter, asymmetric retrieval. This is arguably the most important one for anyone building RIDE pipelines.
For sure. So for the use case of queries versus documents, their input formatting is super simple. They literally prepend the string query or document to the text.
But the real magic is the loss function. It's equation 4 in the paper, the loss cocktail.
The loss cocktail, yeah. It's a linear combination of 3 different losses running simultaneously. The first ingredient is info-NCE,
which is just standard contrastive loss. You pull the positive document close to the query and push the hard negatives away.
Right. Ingredient 2 is distillation loss. They keep the connection to the teacher active here to make sure the student stays aligned with that broader semantic knowledge.
So it doesn't forget general meaning while it specializes in retrieval.
Exactly. But the third ingredient is the really unique one, LGOR, the Global Orthogonal Regularizer.
LGOR. Let's unpack this because it solves a very specific hardware efficiency problem, right?
It does. Sometimes during training, embedding models get lazy. They start clumping all the document vectors into a really narrow cone of the vector space.
So everything looks kind of similar.
Yeah, and LGOR fixes this by forcing the embeddings of non-matching documents to spread out uniformly across the entire unit sphere.
It pushes them as far apart as possible. And the reason this matters so much is for binary quantization.
Exactly. Binary quantization is where you turn 32-bit floating point numbers into 1-bit binary values, zeros and ones.
Which makes your index massively smaller and search speeds incredibly fast.
Right. But if your vectors are clumped together, the differences between them are too subtle. When you compress them to binary, that nuance is destroyed.
So by using LGOR to spread them out, you're effectively pre-optimizing the model to survive that aggressive binary compression.
You're using the full expressive capacity of the dimensions. It's brilliant.
Moving on to the second adapter, text matching, or semantic textual similarity.
This is for symmetric tasks like duplicate detection. The loss function here changes. They use quotient ranking loss, but only if the training data has human-graded scores.
And if it's unranked beta,
then it just falls back to info-NC plus distillation.
Makes sense. Now, the third adapter, clustering, had a really interesting fix, because initially the generic teacher instructions just failed at clustering.
It was too focused on general semantics. So for the clustering adapter, they reran the distillation process, but they gave the teacher model a very explicit instruction.
The prompt was, identify the topic or theme of the given document.
Right. They mathematically forced the student adapter to align with the teacher's specific view of topical groupings, rather than just semantic word overlap.
It's just a really elegant way to build an adapter for a specific intent. Finally, there's the classification adapter.
Yeah, for this one, they convert classification tasks into a triplet format: anchor, positive, negative.
And the loss they use is a bidirectional info-NEE combined with the relational knowledge distillation regularizer.
Which is crucial to prevent feature collapse. It ensures the relative distances between data points are preserved so the model can handle new, unseen classes in zero-shot scenarios.
Okay, so that's the entire pipeline. 2 stages, targeted LoRA adapters, complex loss cocktails. Let's look at the ablation studies to see what actually drove the performance.
Figure 3 in the paper is fascinating here. They compare 3 distillation strategies: info-NC, score-based distillation, and embedding-based distillation.
Score-based is where you just try to match the softmax scores, right? It's a fast way.
Yeah, score-based and info-NC learn really fast. The training curves shoot up early, but they plateau quickly.
They hit a ceiling. Whereas embedding-based distillation, where you're aligning the vectors directly like Gina did, starts a lot slower.
It takes longer to converge, but it keeps improving and ultimately achieves the highest final retrieval performance.
So patience pays off there. And Table 5 breaks down the loss components we talked about.
Right. It proves that relying only on distillation is insufficient. If you remove the task-specific info-NC contrastive loss, your top-tier performance drops.
You really do need that whole cocktail. They also validated the LGOR loss for quantization robustness.
This was a huge finding. Without the GOR loss, performance drops significantly over 3 points when you move from float to binary quantization.
But with GOR included, the drop is minimal, just about 1.9 points.
Which is the difference between a system you can actually deploy at scale and one that just falls apart in production.
Let's talk about the final benchmarks, the MTEB results. How did these tiny models actually fare?
Incredibly well. The small 596M model achieved the highest average score among all small multilingual models.
And the nano? Because 212 million parameters is tiny.
The nano is the real headline. It beats comparable models like Voyage 4 Nano, and crucially, it beats Gemma 300M on retrieval, re-ranking, and STS tasks.
Beating a 300 million parameter model with a 212 million parameter model.
Yeah.
That really validates this whole distillation plus adapter approach.
It does, and on the long context side, they evaluated it on long embed. The small model actually outperforms its own base model, the Qwen 3 0.6b base, on 3 out of the 5 benchmarks.
That's wild. The training regimen actually improved its ability to attend to information over long distances.
And if you compare the student to the 4 billion parameter teacher, it's obviously still a bit worse, but it closes the gap significantly, especially considering the nano is 16 times smaller.
We also need to touch on the Matryoshka efficiency. We mentioned it earlier.
Right, Matryoshka representation learning. The models output a full vector of 1024 dimensions, but they are trained so that the most critical information is packed into the very start of the vector.
So you can just cleanly truncate it. Chop off the end.
Exactly. You can shorten the embeddings down to 256 dimensions, and the performance remains remarkably stable.
And after 256 dimensions.
Then it drops off sharply. But that's entirely consistent with the Johnson-Lindenstrauss lemma, which basically sets the theoretical mathematical limit for how much you can reduce dimensionality while preserving distance.
But having that flexibility built in is massive. If you can store 256 dimensions instead of 1024, you're saving a fortune on cloud storage and RAM for your vector database.
Absolutely. It's a huge operational win.
So summarizing all of this, Jina's V5 approach really proves that you don't need massive parameters to get state-of-the-art results.
You just need a highly sophisticated training pipeline. Distillation, task-targeted LoRA, and those mixed loss functions.
And for anyone listening who wants to deploy this today, the weights are public on Hugging Face. There are quantized versions available for llama.cpp as well.
The barrier to entry is basically zero now. You can run these on edge devices.
Which leaves us with a really provocative thought to end on. The paper clearly shows that generic embeddings are suboptimal compared to these task-specific adapters.
They are.
So does this signal the end of the one-size-fits-all embedding model? I mean, our future architecture is just going to rely entirely on hot swappable adapters for every different API call?
It really seems like that's the direction we're heading. The monolithic embedding model might be a dinosaur.
It's definitely something to explore if you're building out an AI platform right now. Keep reading the papers, everyone. Thanks for joining us on AI Paper Podcasts, and we'll see you in the next deep dive.